Welcome back. My name is Renee Clary, and today we're going to discuss the crustal area for most of our Earth, the seafloor. The seafloor provides great evidence for the theory of plate tectonics, not to mention that it is the repository for most of the sediments that are weathered and eroded from the Earth's surface. Let's get started. There are four major oceans that are considered by most researchers: the Pacific, the Atlantic, the Indian, and the Arctic. There are always some people who say that there is just one major ocean. They're all connected. When we talk about a sea, we're talking about a smaller body of water. This does not mean an evaporated, salty body of water, but a smaller body of water connected to one of the major oceans. A land-enclosed body of water is not considered a sea by our definition. So the Dead Sea is not an actual sea. It's a lake that just happens to be very, very salty. If we take a look at where the water is on the Earth's surface, the hydrosphere, we see that most of the water is in the oceans, 97.2%. So another main reason to study the seafloor is that the seafloor is the bottom of this giant repository for the majority of the water in the hydrologic cycle. As you might imagine, the seafloor has been of interest to scientists for a long time. The HMS Challenger in 1872 through 1876 actually mapped the oceans and collected samples. Look at those dates though, 1872 to 1876. We're not talking about super highly technical research, but they were using what they had available. So they did depth soundings by weighted line. They took some samples from the ocean floor with buckets. And you might remember that when Alfred Wegener proposed his theory of continental drift, he met with a lot of resistance, and some of the resistance had to do with his mechanism, because people knew that continents couldn't plow through ocean basins because the ocean basins were floored by rock, just like the continents were. How did they know that? Partly because of the research of the HMS Challenger. And here is an artist's rendition of the HMS Challenger, again 1872 through 1876. We've come a long way. The deep sea drilling project was initiated in 1968 through the National Science Foundation. The Glomar Challenger was the ship that was used, and during this project they did a lot of things, a lot of research, but they recovered over 1,000 ocean cores from the seafloor. You see a photograph of a core there. Actually, that's half a core. They split it down the length. And you can see the different laminations of mud and clay that are underneath the ocean, the core from the ocean floor. Now, fortunately, when that project ended, the ocean drilling program was initiated in 1985. The Joint Oceanographic Institutions for Deep Earth Sampling, which includes more than one nation, it's a consortium, are part of the ocean drilling program. The ship here is the Resolution, and not only are they sampling from the Resolution, but they're also using submersibles and remotely operated vehicles. Echo sounders and seismic profiling are used instead of those weighted lines back in the 1800s. Here's the research ship, the Resolution. And this is the submersible Alvin. You may have heard of Alvin if you watch some of Bob Ballard's investigations, underwater investigations. He's a famous oceanographer who has investigated the Titanic and other wreckage sites. This diagram shows you how echo sounding works versus the seismic reflection. If we have sound generated from an energy source, it is reflected from the ocean bottom and then it's retrieved back on the ship to give you an idea of the depth of the water. Note with seismic reflection, we're generating a sound source, and the hydrophone trails the ship, and the hydrophone will pick up the reflected sound waves. In addition to coring samples, These clamshell samplers actually take sediments from the ocean floor as well. What about where the sea meets the land above sea level? We have two types of continental margins. A passive continental margin occurs within a plate, while an active continental margin marks where two plates actually meet. We're going to look at the active continental margin first. In an active continental margin, an oceanic plate is subducted beneath a continental plate. There is no continental rise. Instead, we have an oceanic trench that marks that subduction zone. The continental shelf tends to be fairly narrow in active continental margins, and active continental margins are marked by volcanic activity, earthquakes, and mountain building. In this diagram, we're looking at this area right over here on the left-hand side. Note that we have an oceanic plate that is being subducted underneath an overriding continental plate. In this case, the Nazca plate is subducting beneath the South American plate. And note that there are volcanoes and mountains on the overriding continental plate. What about a passive continental margin? Passive continental margins occur within a plate. They don't mark the boundary between two plates. Passive continental margins have broad continental shelves, and they have both a continental slope and a continental rise. We're going to talk in more depth about these terms in just a minute. There is no trench in a passive continental margin because it is not an active plate boundary. Usually the abyssal plains, the long stretches of featureless ocean basin bottom, are more developed in passive continental margins. So if we look back at our diagram, again we're looking at the South American plate. If we look on the right-hand side of that plate, what we see is not an active margin at all, but continental crust transitions into oceanic crust. This is a passive continental margin. Another diagram showing you a passive continental margin. Note that the land above water is going to be to the far left of that diagram. We have a continental shelf that is pretty gently sloping, and then we have a continental slope and a continental rise that is covered by a lot of sediments before we move to the deep ocean basin. Note the transition from oceanic crust to the continental granitic crust underneath the rise. This is an old diagram, but one of my favorites. You have a continental shelf moving from the land, very gently sloping. Note the cross-section of that as well. Look at the different fractures and faults. These are normal faults that are created from divergent activity or tensional stress. We have a slope that marks the end of the shelf, and it is more steeply sloping, for want of a better word. And then we have a developed rise and the abyssal plains. This is a generalized diagram showing both an active continental margin on the left and a passive continental margin on the right. Note that there is a trench and a narrow continental shelf and the absence of a rise in that active margin over to the left-hand side. On the passive margin on the right-hand side, there is a well-developed shelf and a rise. The trench is missing, of course, because it is associated with active margins and subduction. Let's take a look at each of the components, the shelf, the slope, the rise, in a little bit more detail. So, let's start with the continental shelf. It has a very gentle slope. It can vary in width. As we noted, the passive margin tends to have a much wider, more developed continental shelf. It ends at the shelf slope break. where we have a more steeply sloping area moving down to the ocean floor. The average depth of the continental shelf and the shelf slope break is about 135 meters below sea level today. Of course, sea level has fluctuated greatly through geologic time, so that number has changed quite a bit depending on the level of the seas. The continental slope has a steep incline. Submarine canyons mark the slope, and this is where sediment moves through these canyons and it's transported by gravity. I'll show you some pictures of that in just a minute. The sediment is transported through turbidity currents. Turbidity currents are also discussed in the section on sedimentary rocks and sedimentation processes. Turbidity currents are sediment water mixtures, and when they slow down and settle, we end up with a structure known as graded bedding. This is because the heavier particles settle out first, and then the medium-sized particles, and finer until all of the sediment has come out of the water. These deposits accumulate in submarine fans. The continental rise has a gentle slope, just like the continental shelf. The sediment is transported again by gravity. We're looking at turbidity currents. The rise is not present in an active continental margin because we have a trench. In a passive continental margin, the sediment forms a series of overlapping fans and will develop that rise. Let's take a look at that. So here we have a diagram showing the shelf up in the upper part of that diagram. We're moving then down beyond the shelf into a steeper incline. Note the submarine canyon, and the sediments are transported down through turbidity currents, and we have a submarine fan on the bottom where the sediments have come to rest. This diagram shows the results of a turbidity current, though no one witnessed it. In 1929, an earthquake occurred off Newfoundland, and then there were successive breaks of a telephone cable. Yes, this was before satellite communications. Originally, it was thought that the earthquake caused the breaks, but in 1949, scientists who were investigating it realized that the earthquake generated a turbidity current, and it was the turbidity current that moved rapidly along the seafloor and broke the cable. The current traveled about 80 kilometers per hour on the slope, but then slowed to about 27 kilometers on the rise, where the topography flattened out and the momentum was slowed down. Note that the diagram has vertical exaggeration. A lot of these diagrams are not true scale. If no vertical exaggeration is used to display this data, the profile looks like that line, that dark line at the bottom. There it is. Until recently, no one had ever witnessed or photographed a turbidity current. This one was caused by a submarine's propeller, and it occurred near Jamaica. This is one of the first photographs of a turbidity current. Again, an older diagram, but one I really like. Notice that the shelf is very gently sloping, and then we have a very steeply inclined slope, and the lavender flows, the turbidity flows, and the fans are marked at the bottom of the slope. We have those submarine canyons that are developed. The sediment moves rapidly down the slope and the rise, and we end up with the sedimentation on the deep sea floor. Graded bedding results because the heavier particles settle out first. Okay, so there we have that submarine canyon, and the turbidity flow ends at the base where it loses momentum and the sediment is deposited. So how much sediment? Take a look at this photograph, and this is a lot of sediment cascading down a San Lucas submarine canyon off Mexico's coast. So a lot of sediment gets transported beyond the land and ends up on the seafloor, the deep sea floor. If we move into the deep ocean basin, we're looking at something that is dark, cold, very intense pressures. Abyssal plains are large flat areas. Now the seafloor is rugged. We have a rugged topography, but sediment deposition over time will go ahead and bury some of that rugged topography. This map shows the oceanic ridge systems. Those are in yellow. The rift valleys are in red. Note that the abyssal plains, the green areas, we have more of them developed in the Atlantic basin than we do in the Pacific. And here's a profile of the topography and the sediment that covers the topography. If you look at the top surface, it looks pretty darn flat, but there's the original rocky crust underneath, and layers of sediment have slowly masked that rugged topography. Trenches, these are found again in active continental margins. We have two plates that are meeting. A trench is long, narrow. It's the deepest part of the ocean and often associated with volcanoes that make their way above the seafloor. An oceanic ridge, we have volcanic rocks, basalt, and oceanic ridge systems are produced by tensional forces because these are divergent plate boundaries where two plates are pulling apart. The ridges are offset by transform faults. So check out this diagram. You can see the magma below the surface. There are some conduits for the magma, and when the magma actually makes it to the surface, it erupts into pillow lava. Now, what do we know about the eruption? We know that it occurs underwater, because anytime we find pillow lava, this is indicative of underwater eruptions. And note that we have two sections of an oceanic ridge in this diagram. There is one in the upper right, and then if we move over slightly to the left in the lower part, we see the offset segment of that ridge. Note that up at the top on the left side of the ridge, the spreading ridge, we have the crust moving off to the left, but note what happens on the right side of the lower segment of that ridge. We have crust moving off to the right hand side, so left up the top and right over at the bottom. So the area between those two spreading ridges is a transform fault. We have many, many different fracture zones as the ocean basin is stretched and fractures. Black smokers are hydrothermal vents, and this is where the seawater seeps through oceanic cracks. What happens is that water seeping in through the cracks into the ground comes into contact with either magma or hot, cooling igneous rocks, and so that water is heated. It dissolves a lot of minerals, and when the water exits in these black smokers, it has that smoky appearance because of the dissolved minerals. So this diagram illustrates that. Notice that we have the seawater seepage into cracks in the seafloor. We have a magma body not too far from the surface, and as that water is heated, it will dissolve minerals, and when it exits on the seafloor, the mineral-laden water has the appearance of black smoke. So this is a black smoker on the East Pacific Rise. It's about 2,800 meters below the ocean surface. And again, the dissolved minerals give the erupted water a smoky appearance. Now, when we started investigating the ocean floor through submarines and remotely operated vehicles, scientists found a wealth of life forms they never even imagined. It is said that the ocean is one of our last great frontiers. We don't know a lot about the life forms in the ocean basin. These specialized organisms, these are tube worms, they live in areas near black smokers. And to give you an idea, these worms can be about 3 meters long. They're longer than 9 feet in length. Seamounts on the deep ocean floor are underwater volcanoes. And if these volcano summits are eroded flat, we have a guyot. Aseismic ridges are elevated areas, but there is no associated seismic activity. We're not looking at volcanic activity or earthquake activity. They may be the remains or small fragments that were separated from continents during rifting. At least that's what some scientists hypothesize these aseismic ridges are composed of. Okay, here we see a spreading ridge. We see the magma at the base of the cross section, and those two pieces of crust are moving off in opposite directions. Volcanoes form at the ridge, and note that we have a seamount, an underwater volcano, as its top is eroded by the waves. In other words, the building of the volcano does not keep up with erosion, so we have a guyot. Now, what type of sediments are in the deep ocean basin? We have pelagic clays and oozes. Why do you think clay-sized particles are mostly present but not large sand bodies? Remember, we do get some sand bodies through turbidity currents if the sediments are moved from the slope down to the deep ocean basin, but mostly we're looking at clays. So remember that heavier sediments are deposited nearer the shore. So as we move away from the shore, we get typically sand, then silt, clay-sized particles, and finally our carbonates. Although some glacial drop stones are deposited as icebergs melt, most of the deep sea sediment is derived from volcanic ash and wind-blown dust. So pelagic clay are those fine sediments that are derived from continents such as volcanic ash, dust that's carried, and wind currents. The other type of deep sea sedimentation is ooze. Ooze is composed of the remains of microscopic organisms. We can have different types of ooze depending on what types of organisms are responsible. Calcareous ooze is composed of the remains of calcium carbonate skeletons or tests from many tiny organisms that died. Siliceous ooze, on the other hand, is the silica tests of these microscopic organisms that accumulates. This is a foraminifera. It is calcareous. It's a protozoan. What's really remarkable is that this is a one-celled animal that made that beautiful shell. Here are coccolithophores. These are also calcareous, made of calcium carbonate. But we can have siliceous microorganisms as well. These are radiolarans, and if you've ever seen a radiolaran underneath a microscope, it is a wonderful experience. They remind you of those little bitty glass filigree ornaments that you can sometimes buy at those kiosks in the mall, those tiny glass designs, Christmas ornaments. Really neat. But they are composed of silica. And these are diatoms. Diatoms are also composed of silica. Diatomaceous earth is used in a multitude of ways. For example, it's a filtering agent in chemistry. It's also ground into a rock flour, food grade rock flour that's used by some people for health food reasons. It's also a great natural pesticide because the little silica tests puncture the insects walking over it, and great aphid control for some crops. Here is a diagram, a map diagram, showing you some of the different types of ooze in the ocean basins. Note that the calcareous ooze isn't found in cold regions. Look toward Antarctica, for example. You see siliceous ooze. Now, why do you think that's the case? There are calcareous organisms that live in the water above that ooze, but calcium carbonate, unlike many minerals, is more soluble in cold water. So any little organisms that live in the water column, as they die and their little bodies float down, the tests are dissolved, so we don't get calcium carbonate accumulation in very cold areas. It simply dissolves. In addition to our oozes and our pelagic clays, we also have drop stones from melting icebergs. Remember, as icebergs calve off of glaciers, they float out to sea, so any type of sediment that they have either on top or within the ice is released once that ice melts. Cosmic dust is trivial compared to the other sources of sediments. It was once hypothesized to be a much bigger component of deep sea sedimentation, but we know now that pelagic clay is much more important. Chemical precipitates, when the water is heavily saturated with minerals, these chemicals will precipitate out. For example, manganese oxide, manganese nodules precipitate out on the deep seafloor. This diagram will show you the rafting ice. Again, any type of sediment that is included in that ice is slowly released as that ice will melt. So we can get some pretty big pieces farther from land. These are manganese nodules. Okay, let's sort of shift gears and talk a little bit about a fun topic, and that would be reefs. Reefs are mound-shaped structures that are composed of organic remains. A lot of times we think about coral reefs, but there are many, many organisms that are contributing to the structure of that reef. They grow typically 45 to 50 meters below sea level. They don't grow below that depth. They need light and they need clear water. They need warm seas, tropical seas, and they're great indicators of past environments. So if we find fossilized reefs, we can know that the environment in which those reefs grew originally was shallow, tropical, and free of sediments. Reefs don't like sediment, heavy sediment activity. You won't find a coral reef near the Mississippi Delta, for example. The sediments just choke the little filter-feeding organisms. We have different types of reefs depending on their structure. A fringing reef is just what it sounds like. It's attached directly to the margins of a continent or an island. The corals and the other encrusting organisms attach directly to the land. Barrier reefs are reefs that are separated from the land by a lagoon. An atoll, on the other hand, is a circular reef, and we don't see land. It's simply a circular or oval reef in the middle of an ocean. These are formed around volcanic islands, and the volcanic island slowly subsides beneath the wave, and the reef keeps growing until, of course, it can't anchor if the island sinks too far beneath the surface, and then the reef simply erodes away. Here we have a volcano, and I've drawn these little red marks showing you where a fringing reef would anchor directly next to that volcanic island, and the reef would be in that little red area, again directly attached to the island or the continent. Now, if a reef is separated by a lagoon from the island or the continent, we have a barrier reef. I disagree with this diagram. It says fringing reef in the cross section, but the little overhead shot shows a a barrier reef because it is separated by a lagoon. If we look at a good cross section of a reef, we see that we have a lagoonal area in a barrier reef between the reef and the land, and this is where we tend to get carbonate deposition. On the seaside part of that reef, if we go out toward the open sea, we see a talus slope, debris accumulating at the base of the forereef slope. This is a barrier reef. The light colored blue on the inside of the reef is a lagoon, and this one is in the Cook Islands. So what happens if the volcano slowly subsides beneath the waves? The coral keeps building. If it has a carbonate platform upon which to build, it has to keep up in the photic zone. It needs that sunlight in order for the symbiotic algae to photosynthesize. So the reef is left, although the island has now subsided beneath the sea. This is an atoll. And this is an atoll in the Central Pacific Ocean. Now, eventually, if that volcanic island subsides far enough below the sea, the reef cannot keep up with it, and the reef ends up dying. It can't anchor because the island is more than 50 meters below the surface. So at that point, we don't have a reef, but we do have a guyot. We have a flat-top volcano. Interestingly, the first person to recognize the formation of atolls as starting from a fringing reef next to an active volcano, and then a barrier reef, and finally an atoll as the volcano was subsiding beneath the surface of the water, was none other than Charles Darwin. In addition to formulating the theory of organic evolution along with Wallace, he was also quite a geologist. So here we see atolls and Hawaii, and if you look at the little cross section at the bottom of that, you see as the active volcano to the right moves with that conveyor belt further away from the magma source, we have compression of that's probably a poor choice of words. Hotter rocks are less dense than the cooler rocks. So the less dense rocks take up more volume, and therefore as they cool, again, compression is not a good word, but the molecules are much closer together, so our volcano will start to subside as it cools. And especially if we're not active anymore, we're not building that up, we see as we move away from the magma bulge as well that these reefs slowly will have to grow in order to keep up with the sea level. So we will get from fringing to barrier to atoll, and finally as the volcano or island sinks too far beneath the surface, we get a guyot. The final topic in this segment is going to be that of the Exclusive Economic Zone, or the EEZ. It's 200 nautical miles from the U.S. coast, and this was declared by the United States government. And basically what this guarantees the United States of America, it grants us the exclusive right to mineral resources within 200 nautical miles from U.S. coast. That doesn't just include, by the way, the U.S. states, but any territory as well. So this map shows exclusive U.S. rights in blue. The United States claims these for the United States of America, and you'll note that not just the 50 states, Hawaii and Alaska, but American territories as well. What type of resources? Well, maybe manganese nodules one day will be profitable. But in the meantime, petroleum is one resource that's mined under the seafloor in deep water. This is a rig owned by Shell Oil. It's a tension leg rig, and it's anchored in the Gulf of Mexico in, well, actually it's over 1,000 meters of water. Okay, well, that will conclude our discussion today on the seafloor and the types of margins, active and passive continental margins, and the profiles of the seafloor. Thank you so much for joining me. This was meant only as an overview, and there is much more detail in your assigned readings. If you have any questions, please feel free to post them on the discussion board or email your instructor. Thank you for joining me. Have a great day.